The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so yesterday we learned about equations of planes and how to think of 3x3 linear systems in terms of intersections of planes and how to think about them geometrically. And that in particular led us to see in which cases actually we don't have a unique solution to the system, but maybe we have no solutions or infinitely many solutions because maybe the line of intersection of two of the planes happens to be parallel to the other plane. So today, well, we'll start by looking at equations of lines. And so in a way, it seems like something that we've already seen last time because we have seen that we can think of a line as the intersection of two planes. And we know what equations of planes look like. So we could describe a line by two equations telling us about the two planes that intersect on the line. That's not the most convenient way to think about a line usually, though, because when you have these two equations, how do you solve them? Well, okay, you can, but it takes a bit of effort. So instead, there's another representation of a line. So if you have a line in space, well, you can imagine maybe that you have a point on it, and that point is moving in time, and the line is the trajectory of a point as time varies. Okay, so think of a line as the trajectory of a moving point. And so when we think of the trajectory of a moving point, that's called a parametric equation. Okay, so we're going to learn about parametric equations of lines. So let's say, for example, that we are looking at the line through. So to specify a line in space, I can do that by giving you 2 points on the line, or by giving you a point and a vector parallel to the line, for example. So let's say I give you 2 points on the line, -1, 2, 2, and the other point will be, let's say, 1, 3, -1. So, okay, it's pretty good because we have 2 points on that line. Now, how do we find all the other points? Well, there are the points in between these guys and also on either side. Let's imagine that we have a point that's moving on the line. And at time 0, it's here at q0. And in a unit time, I'm not telling you what the unit is. It could be a second, could be an hour, could be a year. At t equals 1, it's going to be at q1. And it moves at constant speed. So maybe at time 1/2, it's going to be here. Time 2, it will be over there. And in fact, that point didn't start here. Maybe it was, it's always been moving on that line. At time -2, it was down there. So let's say q of t is a moving point and at t equals 0, it's at q0. And let's say that it moves. Well, we could make it move in any way we want, but probably the easiest to find. So our goal is going to find formulas for the position of this moving point in terms of t. And we'll use that to say, well, any point on the line is of this form where you have to plug in the correct value of t depending on when it's hit by the moving point. So perhaps it's easiest to do it if we make it move at constant speed. On the line. And that speed is chosen so that at time 1, it's at q1. So the question we want to answer is, what is the position at a time t, so the point q of t? Well, to answer that, we have an easy observation, which is that the vector from q0 to q of t is proportional to the vector from q0 to q1. And what's the proportionality factor here? Yeah, it's exactly t. At time 1, q0q is exactly the same. Okay, maybe I should draw another picture again. I have q0, I have q1, and after time t, I'm here at q of t, where this vector from q0 to q of t is actually going to be t times the vector q0, q1. So when t increases, it gets longer and longer. Okay? So does everybody see this now? Is that okay? Any questions about that? Yes?
Blue is pretty bad from up here.
Okay, so I will try to avoid using blue. Thanks for... that's fine. So, okay, I will not use blue anymore. Okay, well, for this time, let me just make everything white just for now. This is the vector from q0 to q of t. This is the point q of t. Okay, is it kind of visible now?
Yes.
Okay. Thanks for pointing it out. I will switch to brighter colors. So, okay. So apart from that, I claim now we can find the position of this moving point. Because, well, this vector q0, q1, we can find from the coordinates of q0 and q1. So we just subtract the coordinates of q0 from those of q1. We'll get that vector q0, q1 is 2, 1, minus 3. Okay? So if I look at it, well, so let's call x of t, y of t, and z of t the coordinates of the point that's moving on the line. Then we get x of t minus, well, actually plus 1 equals t times 2. Right? I'm writing the components of vector q0, q of t. And here I'm writing t times q0, q1. Y of t minus 2 equals t. And z of t minus 2 equals minus 3t. So in other terms, the more familiar way that we'll use to write these equations, let me do it that way instead, minus 1 plus 2t, y of t equals 2 plus t, z of t equals 2 minus 3t. And if you prefer, I can just say q of t is q0 plus t times the vector q0, q1. Okay? So that's our first parametric equation of a line in this class. And I hope you see it's not extremely hard. In fact, so parametric equations of lines always look like that. X, y, and t are functions of t that are of the form a constant plus a constant times t. The coefficients of t tell us about a vector along the line. Here we have a vector q0, q1, which is 2, 1, negative 3. And the constant terms tell us about where we are at t equals 0. If I plug t equals 0, these guys go away. I get minus 1, 2, 2. That's my starting point. OK. So any questions about that? No? OK, so let's see now what we can do with these parametric equations. So one application is to think about the relative position of a line and a plane with respect to each other. So let's say that we take still the same line up there, and let's consider the plane with equation x plus 2y plus 4z equals 7. Okay, so I'm giving you this plane. And the questions that we're going to ask ourselves are, well, does the line intersect the plane, and where does it intersect the plane? So let's start with first preliminary question that maybe we should try to understand. We have these points, we have this plane, and we have these points q0 and q1. I'm going to draw them in completely random places. Well, are q0 and q1 on the same side of the plane or on different sides, or on opposite sides of the planes? Or could it be that maybe one of the points is in the plane? So I think I'm going to let you vote on that. So is that readable, or is it too small? OK, so anyway, the question says, relative to the plane x plus 2y plus 4z equals 7, these points q0 and q1, are they on the same side, on opposite sides? Is one of them on the plane? We can't decide. OK, should be better. So I see relatively few answers. OK, it looks like also a lot of you have forgotten their cards. And so I see people raising 2 fingers. I see people raising 3 fingers. And I see people raising 4 fingers. I don't see anyone answering number 1. So the general idea seems to be that either they're on opposite sides or maybe one of them is on the plane. Well, let's try to see. Is one of them on the plane? Well, let's check. OK, so let's look at the point. Sorry, I have one more blackboard to use here. So if I take the point q0, which is at minus 1, 2, 2, well, if I plug that into the plane equation, so x plus 2y plus 4z will equal minus 1 plus 2 times 2 plus 4 times 2. That's, well, 4 plus 8, 12, minus 1, 11. That, I think, is bigger than 7. OK, so q0 is not in the plane. let's try again with Q1. 1, 3, negative 1. Well, if we plug that into x plus 2y plus 4z, we'll have 1 plus 2 times 3 makes 7, but we add 4 times negative 1. We end up with 3 less than 7. Well, that one is not in the plane either. So I don't think, actually, that the answer should be number 3. So let's get rid of answer number 3. OK. Let's see. In the light of this, are you willing to reconsider your previous answers? And OK, so I think now everyone seems to be interested in answering number 2. And I would agree with that answer. So let's think about it. These points, they're not in the plane, but they're not in the plane in different ways. One of them somehow overshoots. We get 11. The other one, we only get 3. That's less than 7. If you think about how a plane splits space into 2 half spaces on either side, well, one of them is going to be the points where x plus 2y plus 4z is less than 7. And the other one will be, so that's somehow this side, and that's where Q1 is. And the other side is where x plus 2y plus 4z is actually bigger than 7. And to go from one to the other, well, x plus 2y plus 4z needs to go through the value 7. If you're moving along any path from Q0 to Q1, this thing will change continuously from 11 to 3. At some time, it has to go through 7. Does that make sense? So to go from Q0 to Q1, we need to cross P at some place. So they're on opposite sides. OK. Now, that doesn't quite finish answering the question that we had, which was, where does the line intersect the plane? But well, we can do the same thing. Now we know not only the points Q0 and Q1, we know actually any point on the line, because we have that parametric equation up there telling us where is the point that's moving on the line at time t. So what about the moving point Q of t? Well, let's plug its coordinates into the plane equation. So we'll take x of t plus twice y of t plus 4z of t. Okay, that's equal to, well, minus 1 plus 2t plus twice 2 plus t plus 4 times 2 minus 3t. So if you simplify this a bit, you get 2t plus 2t minus 12t. That should be minus 8t. And the constant term is minus 1 plus 4 plus 8 is 11. Okay, and we have to compare that with 7. Okay, question is this ever equal to 7? Well, so Q of t is in the plane exactly when minus 8t plus 11 equals 7. And that's the same. If you manipulate this, you will get t equals 1/2. Okay. In fact, that's not very surprising. If you look at these values, 11 and 3, you see that 7 is actually right in between. It's the average of these two numbers. So it would make sense that it's halfway in between Q0 and Q1 that we will get 7. Okay. And then at that time, Q at time 1/2, well, let's plug the values. So minus 1 plus 2t will be 0. 2 plus t will be 2.5, or 5 halves. And 2 minus 3 halves will be 1 half. Okay? So this is where the line intersects the plane. So you see that's actually a pretty easy way of finding where a line and a plane intersect each other. If we can find a parametric equation of the line and an equation of the plane, then we basically just plug one into the other and see at what time the moving point hits the plane. And then we know where it is. OK, are there questions about this? Yes? Sorry, can you say that? Yes. So what if we don't get a solution? What happens? So indeed, our line could have been parallel to the plane, or maybe even contained in the plane. Well, if a line is parallel to the plane, then maybe what happens is that when we plug in the positions of a moving point, we actually get something that never equals 7, because maybe we get actually a constant. Say that we had gotten, I don't know, 13 all the time. Well, when is 13 equal to 7? The answer is never. Okay, so that's what would tell you that the line is actually parallel to the plane. You would not find a solution to the equation that you get at the end. Yes? So if there's no solution at all to the equation that you get, it means that at no time is the traveling point going to be on the plane. That means the line really does not hit the plane ever. So it has to be parallel outside of it. On the other hand, if the line is inside the plane, then that means that no matter what time you choose, you always get 7. Okay, that's what would happen if a line is in the plane. You would always get 7. So maybe I should write this down. So if a line is in the plane, then what do I want to say? When we plug x of t, y of t, z of t into the equation, we always get well, here in this case, 7 or whatever the value should be for the plane. Okay. If the line is parallel to the plane, in fact, we get, I should say, another constant. So in fact, when you plug these things, normally you get a quantity that's of the form something times t plus a constant, because that's what you plug into the equation of a plane. And so in general, you have an equation of the form something times t plus something equals something, and that usually has a single solution. And the special case is if this coefficient of t turns out to be 0 in the end, and that's actually going to happen exactly when the line is either parallel or in the plane. In fact, if you think this through carefully, the coefficient of t that you get here, see, it's 1 times 2 plus 2 times 1 plus 4 times minus 3. It's the dot product between the normal vector of the plane and the vector along the line. So see, this coefficient becomes 0 exactly when the line is perpendicular to the normal vector. That means it's parallel to the plane. So everything makes sense. Okay, if you're confused about what I just said, you can ignore it. Okay, more questions? No? OK, so if not, let's move on to more general parametric equations. So I hope you've seen here that parametric equations are a great way to think about a line in space. They're also a great way to think about actually any curve, any trajectory that can be traced maybe by a moving point. So more generally, we can use parametric equations for arbitrary motions in the plane or in space. So let's look at an example. Let's take, so it's a famous curve called the cycloid. And the cycloid is something that you can actually see sometimes at night when people are biking if they have something that reflects light on their wheel. So let me explain what's the definition of the cycloid. So I should say I've seen a lecture where actually the professor had a volunteer on a unicycle to demonstrate how that works. But I didn't arrange for that. So instead, I will explain it to you using more conventional means. So let's say that we have a wheel that's rolling on a horizontal ground. And as it's rolling, of course, it's going to turn. So it's going to move forward to a new position. And now let's imagine that we have a point that's been painted red on the circumference of a wheel. And initially, that point is here. Okay? So as the wheel starts rotating, well, of course, it moves forward, and it turns on itself. So that point starts falling back behind the point of contact, okay, because the wheel is rotating at the same time as it's moving forward. And so the cycloid is the trajectory of this moving point. Okay, so the cycloid is obtained by considering, so we have a wheel, let's say of radius a. Okay, so this height here is a, rolling on a floor, which is the x-axis. And let's, sorry. And we have a point P that's painted on the wheel. Initially, it's at the origin. But of course, as time goes by, it moves on the wheel. So P is a point on the rim of a wheel. And it starts at the origin. So the question is, what happens? In particular, can we find the position of this point, x of t, y of t, as a function of time? Okay. So here's the reason why I have this computer. So I'm not sure if it will be very easy to visualize, but so we have a wheel. Oh, that's not very well. I hope you can vaguely see that there's a circle that's moving. The wheel is green here. And as you know, there's a radius that's been painted blue on it, and that radius rotates along the wheel as the wheel is moving forward. So now let's try to paint actually the trajectory of the point. OK, so that's what a cycloid looks like. OK, so the cycloid, well, I guess it doesn't quite look like what I've drawn. It looks like it goes a bit higher up. But it will be the trajectory of this red point. And see, it hits the bottom once in a while. It forms these arches because, well, when the wheel has rotated by a full turn, then you're basically back at the same situation, except a bit further along the road. Okay, so if we do it once more, see, the point now is at the top, and now it's at the bottom, and then we start again, it's at the top, and then again at the bottom. OK. No. OK, so the question that we want to answer is, what is the position x of t, y of t of the point P? OK, so actually, I'm writing x of t, y of t. That means that I have, maybe I'm expressing the position in terms of time. Let's see, is time going to be a good thing to do? Well, certainly the position changes over time. But does it actually matter how fast the wheel is rolling? No, because I can just play the motion in fast forward. The wheel will be going faster, but the trajectory is still the same. So in fact, time is not the most relevant thing here. What matters to us more is how far the wheel has gone. So we could use as a parameter, for example, the distance by which the wheel has moved. Or we can do even better, because we see that really the most complicated thing that happens here is really the rotation. So maybe we should actually use the angle by which the wheel has turned to parameterize the motion. Okay, so there's various choices, and actually you can choose whichever one you prefer. But I think here we'll get the simplest answer if we parameterize things by the angle. So in fact, instead of t, I will be using, let's call theta, as a function of the angle theta by which the wheel has rotated. So how are we going to do that? Well, because we are going to try to use our new knowledge, let's try to do it using vectors in a smart way. So let me draw a picture of a wheel after things have rotated by a certain amount. So maybe my point P now is here. And so the wheel has rotated by this angle here. And I want to find the position of my point P. Okay? So the position of this point P, that's going to be the same as knowing the vector OP from the origin to this moving point. So I haven't really simplified the problem yet, because we don't really know about vector OP. But maybe we know about simpler vectors whose sum will be OP. So let's see. Let's give names to a few other points in there. For example, let's say that this will be point A, A is the point where the wheel is touching the road, and B will be the center of the wheel. Then it looks like maybe I have actually a chance of understanding vectors like maybe OA doesn't look quite so scary, or AB doesn't look too bad, BP doesn't look too bad, and if I sum them together, I will obtain OP. So let's do that. So now we've greatly simplified the problem. We had to find one vector that we didn't know. Now we have to find 3 vectors that we don't know. But you'll see each of them is actually fairly easy to think about. So let's see. Should we start with vector OA, maybe? So OA has 2 components. One of them should be very easy. Well, the y component is just going to be 0, okay? It's directed along the x-axis. What about the x component? So OA is the distance by which the wheel has traveled to get to its current position. Yeah, I hear a lot of people saying r theta. I mean, let me actually say a theta, because I've called a the radius of the wheel. So this distance is a theta. Why is it a theta? That's because the wheel, well, there's an assumption, which is that the wheel is rolling on something normal, like a road, and not on maybe ice or something like that. So it's rolling without slipping. So that means that this distance on the road is actually equal to the distance here on the circumference of the wheel. This point P was there, and the amount by which things have moved can be measured either here or here. These are the same distances. Okay? So that makes it a theta, and maybe I should justify by saying amount by which the wheel has rolled, has moved, it's equal to so the distance from O to A is equal to the arc length on the circumference of the circle from A to P. And you know that if you have a sector corresponding to an angle theta, then its length is A times theta, provided that, of course, you express the angle in radians. That's the reason why we always use radians in math. Okay. Now, let's think about vector AB and vector BP. Okay, so AB is pretty easy, right? Because it's pointing straight up, and its length is A. So it's just 0, A. Okay. Now, the most serious one we've kept for the end, what about vector BP? So vector BP, we know 2 things about it. We know actually its length. So the magnitude of BP is A, and we know it makes an angle theta with the vertical. So that should let us find its components. Let's draw a close-up picture. Now, in a picture where I'm going to center things at B. So I have my point P. Here I have theta. This length is A. Well, what are the components of BP? Well, the x component is going to be almost. I hear people saying things about A, but I agree with A. I hear some cosines, I hear some sines. I think it's actually the sine. Yes, it's A sine theta, except it's going to the left, so actually it will have a negative A sine theta. Okay? And the vertical component, well, it will be A cosine theta, but also negative because we are going downwards. So it's negative A cosine theta. So now we can answer the initial question, because vector OP, well, we'll just add up OA, AB, and BP. So the x component will be A theta minus A sine theta, and A minus A cosine theta. Okay. So any questions about that? Okay, so I claim that's the answer because this thing here is the x coordinate as a function of theta, and that one is the y coordinate as a function of theta. So now, just to show you that we can do a lot of things when we have a parametric equation, here's a small mystery. So what happens exactly near that bottom point? What does that curve look like? You know, the computer tells us, well, it looks like it has some sort of pointy thing. But is that something on the display? Or is it actually what happens? So what do you think happens near the bottom point? Remember, we had that picture. Let me show it once more. Where you have these corner-like things at the bottom. Well, actually, is it indeed a corner with some angle between the two directions? Does it make an angle? Or is it actually a smooth curve without any corner, but we don't see it because it's too small to be visible on the computer screen? Does it actually make a loop? Or does it actually come down and then back up without going to the left or to the right and without making an angle? So yeah, I see majority votes for answers number 2 or 4. And well, at this point, we can't quite tell. So let's try to figure it out from these formulas. I mean, really, the way to answer that for sure is to actually look at the formulas. Okay, so question that we are trying to answer now is what happens near the bottom point. Okay, so how do we answer that? Well, we should probably try to find simpler formulas for these things. Okay, so well, to simplify, maybe let's divide everything by a. Let's rescale everything by a. If you want, let's say that we take the unit of length to be the radius of our wheel. So instead of measuring things in feet or meters, we'll just measure them in wheel radius. So take the length unit to be equal to the radius. So that means we'll have a equals 1. Then our formulas are slightly simpler. We get x of theta is theta minus sine theta, and y equals 1 minus cosine. Okay, so if we want to understand what these things look like, maybe we should try to take some approximation. Okay? So what about approximations? Well, probably you know that if I take the sine of a very small angle, it's close to the actual angle itself, if theta is very small. And you know that the cosine of an angle that's very small is close to 1. Well, that's pretty good. If we use that, well, we'll get theta minus theta, 1 minus 1. It looks like it's not precise enough. We just get 0 and 0. That's not telling us much about what happens. Okay, so we need actually better approximations than that. So hopefully you have seen in one-variable calculus something called Taylor expansion. That's OK. I see that OK, so if you have not seen Taylor expansion, or if somehow it was so traumatic that you've blocked it out of your memory, let me just remind you that Taylor expansion is a way to get a better approximation than just looking at the function and its derivative. So and here's an example of where it actually comes in handy in real life. So Taylor approximation says that if t is small, then the value of a function f of t is approximately equal to, well, our first guess, of course, would be f of 0. That's the roughest approximation. If we want to be a bit more precise, we know that when we change by t, well, t times the derivative comes in. That's the linear approximation to how the function changes. Now, if we want to be even more precise, then there's another term, which is t squared over 2 times the second derivative. And if you want to be even more precise, you'll have t cubed over 6 times the third derivative at 0. Okay? And you can continue and so on, but we won't need more. So if you use this here, it tells you that sine of a small angle theta, well, yeah, it looks like theta, but if we want to be more precise, then we should add minus theta cubed over 6. And cosine of theta, well, it's not quite 1. It's close to 1 minus theta squared over 2. Okay, so these are slightly better approximations of sine and cosine for small angles. So now if we try to figure out, again, what happens to our x of theta, well, that will be theta minus theta cubed over 6. That's theta cubed over 6. And y, on the other hand, is going to be 1 minus that. That's about theta squared over 2. So now which one of them is bigger when theta is small? Yeah, y is much larger. Okay, if you take the cube of a very small number, it becomes very, very, very small. So in fact, we can look at that. So let me say, x in absolute value is much bigger. It's much smaller than y. And in fact, what we can do is we can look at the ratio between y and x that tells us the slope with which we approach the origin. So y over x is, well, let's take the ratio of these two. That gives us 3 divided by theta. That tends to infinity when theta approaches 0. So that means that the slope of our curve near the origin is actually infinite. And so the correct picture is really something like this. Okay. So the instantaneous motion, if you had to describe what happens very, very close to the origin, is that your point is actually not moving to the left or to the right along with the wheel. It's moving down and then up. And of course, I mean, at the same time, it is actually moving a little bit forward at the same time. But the dominant motion near the origin is really that it goes down and then up. So answer number 4, you have a vertical tangent. OK. I think I'm at the end of time. So have a nice weekend. And I'll see you on Tuesday. So on Tuesday, I will have practice exams for next week's test.